Hello, I'm Matthew Schofield, and I will be presenting a new literature-based discovery application using the PubMed database. This project is a collaboration between the Department of Computer Science at Rowan University and the Department of Cell, Developmental, and Regenerative Biology at the Icahn School of Medicine at Mount Sinai. This project is overseen by Dr. Gabriela Haristescu and Dr. Rulian Radu. A quote that speaks to the thesis of literature-based discovery is, "All the secrets of the world worth knowing are hiding in plain sight," by American author Robin Sloan. Perhaps all is a strong sentiment, though many valuable connections lie in plain sight unrecognized. Novel, verifiable hypotheses are critical to scientific advancement. Valuable connections between seemingly unrelated fields lie undiscovered. Artificial intelligence can help us find these connections in a process known as literature-based discovery, or LBD. Researchers can be empowered by LBD tools to find connections between the over 30 million biomedical papers PubMed allows access to. This idea was pioneered by Don R. Swanson in Undiscovered Public Knowledge, published in the Library Quarterly in April of 1986. In Undiscovered Public Knowledge, Swanson highlights the relationship between fish oil and Raynaud's disease. In the medical literature, it was known that high blood viscosity is common in those with Raynaud's disease. It was also known that fish oil lowers blood viscosity. However, it had not yet been tested whether fish oil could alleviate symptoms of Raynaud's disease. It is now accepted that fish oil provides some symptomatic relief to those suffering from Raynaud's disease. This is an example of a causal chain where A causes B, B causes C. Could A cause C? Our goal was to unlock more of these hidden connections using modern technologies. We present a system to extract causal chains from over 30 million biomedical abstracts accessible through PubMed, and have developed a cloud-based web application to explore these connections. Either our database of extractions can be used with preset parameters we have chosen, or the PubMed API can be used directly to access abstracts and extract SPOs with differing parameters. Here is a diagram of our causal chain extraction process. We will now be referring to causal chains as subject-predicate-object relationships, or SPOs. The first step is to use the tokenization model within the natural language processing package spaCy to tokenize the text of a given abstract from PubMed and apply part-of-speech tagging. We then search the tokenized text for actionable words that exist in a given list. For example, words such as causes, increases, reduces, etc. Once the actionable words within an abstract text are located, we search for the subject and objects that they apply to. We add additional weight to related mesh terms. Mesh terms refer to terms in the medical subject headings thesaurus, which are highly relevant terms in the life sciences, such as antioxidants, coenzymes, pathology, etc. This process produces many SPO relationships. We then use a list of the most frequent words used in medical text, which we generated from analysis of the over 30 million PubMed abstracts to remove overly common words from the generated relationships to reduce non-meaningful results. The output is a list of SPO relationships that are believed to be meaningful that are found within the abstract's text. Here's the page to prepare a query in our system using our prepared database. This gives standard options similar to many scholarly search tools. There is a section where a user can define query terms with the option to use Boolean operations and target specific fields. The number of abstracts to access can also be selected. These will later be compared between each other and the entire database. A date range can also be specified to only access materials published within the specified dates. This is the Advanced API-based query page. If a user wishes to apply additional filtering parameters rather than the default parameters we used in creating our database. On this page, the number of common words to exclude can be selected. For example, if 1000 is selected, then the top 1000 most frequent words will be removed from the generated SPOs. One or more proximity filters can also be specified, where only abstracts that have specific phrases within some number of words of each other will be used. We can use SPOs from differing abstracts to create ABC causal chains, where the AB is the subject and object of an SPO from abstract 1 and BC is the subject and object of an SPO from abstract 2, where the object from SPO 1 matches the subject in SPO 2. Below is shown a representation of an ABC chain where we have related SPOs from two different abstracts. The AB to BC SPO relationship is shown, and then the sentences where each SPO originates from are shown so the user can have a better idea of each SPO's context. The query results page is divided into three sections. First, the ABC chains generated from comparing SPOs within the set of abstracts retrieved by the query are shown. Then the ABC chains generated from comparing SPOs within the query to SPOs from the database of SPOs generated from all of PubMed are shown. The final section lists all abstracts retrieved by the query and the associated SPOs produced by them. A user can also execute a comparison query by selecting two queries by their ticket identifiers. All queries are tracked by tickets which have randomly generated identifiers, which are of length 3 and contain letters and numbers. The SPOs from within each query connected to each ticket will be compared to generate ABC chains. This allows for a specific search for connections between two domains. The result page for a comparison query has two sections. The first has ABC chains where the AB portion SPOs are generated from the query associated with ticket 1, and the BC portion SPOs are generated from the query associated with ticket 2. The second section is the inverse of this, where the AB portions are comprised of SPOs from ticket 2 and the BC portions are comprised of SPOs from ticket 1. In A Survey on Literature-Based Discovery Approaches in Biomedical Domain, Gopala Krishnan et al. Present four types of LBD approaches. Co-occurrence-based methods, where co-occurring B terms are sought after to connect texts containing A-B relationships and texts containing BC relationships. These are relationships similar to the classic Don Swanson example of fish oil and lower blood viscosity and Raynaud's disease. Semantic relation-based approaches are where specific semantic structures are searched for example, subject-verb-object patterns, to discover relationships. Graph-based approaches build complex relationship graphs within a set of biomedical text to attempt to find unseen relationships. These approaches often require human intervention and fine-tuning, though they are better equipped to find more complex and relationships. Lastly, there are hybrid approaches, which combine the previously mentioned approaches. Our approach would be considered a hybrid approach between co-occurrence and semantic relation. We identify subject-predicate-object relationships and then connect them as ABC model chains. Here is an example ABC chain produced by our system. The first abstract contained the text, sevoflurane treatment significantly increased the calcium 2 plus concentration, which produced the SPO, sevoflurane increased calcium 2 plus. The second abstract contained mitochondrial calcium 2 plus overload can damage mitochondria recycling via mitophagy. This generated the SPO, calcium 2 plus, damage mitochondrial recycling. This ABC chain suggests that the hypothesis, does sevoflurane damage mitochondrial recycling, is worthy of testing. Here is our system's performance on the LBD classic example presented by Swanson between fish oil and Raynaud's disease. Our first input is dietary fish oil lowers blood viscosity, reduces platelet aggregation, and inhibits vasoconstriction. This produces the SPO fish oil lower blood viscosity. Our second input, lower blood viscosity, reduced platelet aggregation, and inhibition of vasoconstriction prevent Raynaud's syndrome, produces the SPO lower blood viscosity, prevent Raynaud's syndrome. Our system is able to successfully identify and present the testable hypothesis that is it the case that fish oil prevents Raynaud's syndrome. In conclusion, we have created a cloud-based, literature-based discovery platform. This utilizes deep learning to power natural language processing to extract causal relationships from the over 30 million biomedical texts PubMed allows access to. This empowers researchers to explore and find hidden connections between various domains. There are many opportunities for future work. Some examples are an improved methodology to extract more complex and reliably useful causal chains. As well, the creation of a tokenization and part-of-speech model targeted specifically to biomedical literature. Additionally, a user rating system to train the platform on what types of connections produce meaningful results. These would all be useful components moving forward. We would like to acknowledge and thank Rowan University, as this work was supported by the All About Meaningful Employment grant through Rowan University, and additional support was provided by the Rowan University's Department of Computer Science, allowing us to use their AWS Cloud server time. Please leave any questions or comments in the comment section of this video, or send them to my email at scofieldm0@students.rowan.edu as shown on the screen. Thank you.